The next project that we are going to be presenting is interesting because we actually did collaborate with Victoria last summer, but the depth of the data we had barely scratched, and there was all these really cool things, and even some analogies with the things that's happening with March 2020 and some of the missions happening from JPL that we thought it would be an interesting challenge for us and for our interns to actually do a follow-up on the project and see if we could take a different direction and just kind of go a little deeper. Now we'll hand over to our students to talk about DEEPSEE and the work they did on studying the ocean microbiology and biochemistry based on sample course.
Great, thanks, Santiago. Hey everyone, so in case there are any new joiners, I will reintroduce myself. My name is Noah Deutsch. I'm one of the design interns on this project, and I'm a master's student in design engineering at Harvard University.
And I am Malika, the other design intern on the project, and I'm a master's student at CMU.
Hey, and I'm Adam. I was the computer science intern for this project developing the tool, and I'm currently a PhD student in human-centered computing at Georgia Tech.
And we're excited to talk to you about DEEPSEE. You know, we couldn't have gotten here without our amazing collaborators, Victoria, John, Haley, and the ORPHAN lab team. And DEEPSEE is a really cool tool that's helping us interpolate sparse data to guide DEEPSEE core sample site selection. And like the other project, we're going to give you a little bit of a sneak peek, and now we're going to zoom out and talk about the problem space and how we arrived here. So we've been working very closely with the scientists at CALTECH's ORPHAN lab, who are actively studying the microbial communities that live around methane seeps at the bottom of the ocean. These communities are really important because they consume a lot of methane that's coming out of these seeps. And by consuming that, they're preventing it from reaching the atmosphere and contributing to climate change. So it's really important that we study these communities and understand how we can keep them healthy. But studying these communities is really challenging. To do this, scientists have to survey the ocean floor. They have to draw core samples using underwater robots. And as you can imagine, this is a very time-consuming and expensive process. And so a very, very limited number of samples can be taken. But from the samples and the data we do collect, it's very rich data. There's this sort of pre-dive mapping data where we can look at bathymetry and understand the topological features. We can get a sort of photomosaic data and understand the sort of surface expression and what's actually happening. And what you're seeing is this very beautiful microbial map at the bottom of the ocean. And then, of course, we can take these core samples, and from that, these are taken at different horizons of depth. And from that, we can extract geochemistry and microbial data to understand sort of the composition and what's living at these different horizons. One of the challenges is that the cost associated with taking these samples creates very strong incentives to pick obvious spots where there is a visible surface expression of the microbial community, such as the microbial map that I just showed. And what we've heard is that samples taken outside of these areas are a lot less likely to have scientific value. But this comes at a cost. You know, by sort of only picking these obvious spaces, it limits scientists' ability to understand the true bounds of where these important microbes live and how their sort of area of influence is changing over time. So our task that we've given ourselves for the summer for this project is to help scientists make more informed sample site selections and really focusing on these non-obvious locations in order to help them illuminate the edges of microbial activity around these methane seeps. Similar to before, we followed a very iterative process beginning with contextual inquiry, where we were sort of working very closely with the scientists to understand their current tools, their workflows, and their needs, and then followed this sort of 10-week iterative process of design and data exploration, followed by user testing and refinement to ultimately end up at today's prototype. And similarly, we explored a lot of different directions. I think for this project in particular, you know, we learned very early on that sort of showing the interpolated data in 3 dimensions was really helpful in terms of helping the scientists build spatial intuition about the distributions, which we'll talk more about in a little bit. And our solution is DEEPSEE. And what DEEPSEE does is provides a platform to generate and visually explore 3-dimensional interpolations between this sparse core data, sort of all with the goal of guiding future sample site selection. And just to break that down, you know, by interpolating, what we're doing here is sort of drawing lines and filling gaps within the data to identify previously invisible hotspots of activity. We're then allowing scientists to visually explore this generated data in 3 dimensions, allowing them to build that spatial intuition. And lastly, sort of the goal of all this is to help guide future sample site selection. So that means incorporating a lot of other contextual information and data that they need to make these decisions, including some of that bathymetry and photomosaic data that I was showing before. And there are really sort of 2 primary use cases that we're thinking for this tool. And we focus mostly on the first, but we think it has a lot of legs for the second. And the first is pre-cruise planning, simply identifying promising sample sites in advance of an upcoming research cruise. And the second is actually the sort of during cruise refinement, where they're able to interpolate on the fly with data that's collected right before a dive occurs. And we've heard that this might be really useful with temperature data in particular. Now I'll hand it over to Adam to give a demo of the tool that he built.
Great. Can everyone hear me? You guys know you guys can hear me? Great. All right. Screen should be shared. What you're seeing now is a live demo of the tool. I'm gonna make it full screen. Perfect. So let's go through this scenario and let's imagine that I am a new researcher in the ORPHAN lab, tasked with understanding the data that's previously collected, because I'm going to be part of planning for a new cruise coming up, and I want to help with this sample site selection. For the example, let's assume we're going back to a place known as Pescadero, which is already loaded in. And what we're already seeing is one of the maps that was generated for that location on a previous dive. This is going to be a topography map right here. So without knowing anything, I think I'm going to go in and investigate, again, what data was collected. I'm going to zoom in here. And what I'm seeing is we've got plotted the prior collected cores that comes from our data set on top of the topographic data. This is really important because it's going to tell me where spatially all the information is located, and immediately draw my eye to a large cluster of cores down here. There must have been a reason that these were collected here, so I might want to understand this further. So once again, I'll zoom in a little further. And now I'm starting to get a better picture of what the geography looked like, where there might be rocks, large ridges. This is really interesting, but I'm missing that contextual information of the photomosaic. What did the seafloor actually look like? So while we're investigating this region of interest, I can on the fly switch over to a photomosaic map and see in the same space what the actual seafloor might have looked like in terms of where the organisms are located. This is already giving me so much more information, because now I can see that there were actually microbial mats in this location, hence why they probably collected a lot of cores there. And this is going to lead me to say, well, how about I look on top of the mats? This is probably a good place to see what data was collected about the organisms in that area. So I'll probably zoom into this location here, which is giving me a good view of these 5 cores in the center here. And what next I'll probably do and spend a lot of time doing is annotating. That is, I'm probably going to take some notes on the map, for example, drawing the outline of this map, so I can start to collaborate with my team and explain to them what I'm looking at, as well as taking screenshots and taking notes about anything I'm seeing on this image here. So while I've outlined this map, what I'm missing now is how this relates, and once again, to the geography. So once more, we can flip back. And interestingly enough, we can see that the mats almost follow the edge of this ridge here. There were some rocks over in this location, and what looks to be like a little mound in the center of the mat. This is really important for us to understand. It almost looks like there's a sphere of influence, an area that these microbes are inhabiting, and the data was collected in a certain region, sometimes outside of the mat and sometimes inside of the mat. So as I go through, this can be done for any location, but for the sake of the presentation, let's assume I've decided that these are really interesting cores. I'll go in and I will select cores of interest, which will immediately update the right panel. At this point, now I'm looking at a core view and it's telling me to select a variable. So let's look at a variable of interest from my data set, for example, sulfide. What this view is giving me right now is the breakdown visually of the values in each of the cores. So immediately I'm greeted with the cores that have data and that don't have data. I can do this for any number of attributes that I might be interested in, pH. Once again, we're seeing a similar pattern. Some of them don't have data. So this is helping me to pre-process. I can actually remove these now, which updates my selection on the left panel automatically, and probably just keep the 3 that have data associated with them. Now that I've chosen the cores that I really want to focus on, I can move over to the interpolation. So I move over to the interpolation view. It's telling me to select my attributes, so I'll choose sulfide again, and then interpolate. We explained interpolation a little bit, but essentially we're trying to fill in data in the space on the map where there is no data. We have 2 ways of doing this. One is a natural, which is a space filling extrapolation. It takes the values and extrapolates them. Or linear, which draws lines between the points and fills them in with values. I'm going to go with natural because I want to see what the whole region might look like. And I can choose my resolution. These cores are 7 centimeters in diameter. So I'll go with 7 centimeters to see the most resolved view I can get. What I'm greeted with is the 3D interpolation, the space-filled 3-dimensional view of what the values of sulfide might look like in this entire space. The first thing I'll probably want to do is get a view of what it actually looks like there. So I can turn off the interpolation and make these cylinders. And now this is the data plotted in 3D. This is really awesome, but it's kind of hard to see each of these boundaries because the region is so large. I can blow that up a bit. And now I'm starting to really see, okay, those values that I saw in the core view, now I can see them plotted in 3 dimensions here, which is really giving me depth and spatial information. So I'll probably go through now as the researcher and start comparing attributes. Turn back on the interpolation, and I might want to start seeing these patterns emerge in 3D. For example, I'll go see pH. And once again, we're starting to see almost an inverted pattern with this color scheme, where pH is low in the same place that sulfide was high. This is really interesting. We are looking for places where there's gradient drop-offs that are very steep. That means the colors in this representation, the colors will change very rapidly. That's very important to pick up on because we want to see if any of the organisms there are affecting the geochemical processes that are happening. So now that I've identified an area, it almost looks like this corner here, right? Which relates, if I look at the horns here, it looks like it relates to this point in the top left. It almost appears to me as if this area is showing a lot of activity and not as much in the other areas from the collected cores. Not as much activity might be going on there. So this is already telling me that if we're going to sample somewhere new, I might want to start investigating where I'm seeing the data changing very frequently. And now I can do that spatially. I can say, okay, towards the top left of this object, which is in this area, there might be something interesting. I can switch over to my photo mosaic, and suddenly we see the value here clearly shown that there's no microbial mat in that location, yet it almost seems like the values are changing towards that location. So before, we would never have known to sample in this location without a microbial map because there's no surface expression. But with the data plotted in 3D, we get a sense that there might actually be transitions under the surface of the data moving in that direction. So I can take my annotations on the map. I can show this to my team and say, hey, oh, we want to go back here. I want to show this to my team and say, hey, maybe we want to sample right here. This would be really important. So the last step that we have in this process to make sure the team has enough information is to select. I can go in and select any samples here. So let me give a good view of that. I probably want to select samples over here and get some of the interpolated data out of this object. So I can select a column of interpolated data, which automatically populates a list here. So I can probably choose 2 or 3 over here, right? This is going to give me latitude and longitude of locations I might want to sample and the data that I might want to check. And the last step is to export it all out. And suddenly now I have a JSON file, which has all of that interpolated data that I can compare, give to the researchers, give to the divers. And I've done all this in minutes without knowing anything about this region. So it did a lot for me to see it visually rather than just in a spreadsheet without any geographic information. And at this point, we're going to turn it back over to the slides to go over some of the architecture of the tool. So I will, there you go, perfect. So for those of you who want to do this yourselves or want to know how we did this, right now it's running the back end. There's a front end and back end. The back end server is running Python, which is receiving the data from the CSV from the front end, and it's generating XYZ plotted data for the interpolations, which is going to 3JS in the front, which I'll explain in a bit. But there's nothing more really going on in the back end. It's a bunch of Python processing each object. The front end was built with Vue to scaffold the whole thing. And it's styled by Vuetify. It's a material design framework, so it looks pretty nice. And the final tool is actually going to be wrapped into a standalone Electron desktop app. What this means is that it's going to be an application you might find on any computer that you have that you just kind of double click and boom, it opens up. So that the team can take this with them on the dives if they want to. They don't have to be connected to the internet. This is going to be really big where on the dives they don't have internet or have very limited internet. So having this be portable is a very big win for us. And finally, the visualizations themselves. D3, you're going to notice a pattern here. D3 is very, very useful for plotting data. We do this with the 2D data, where we have the maps that we scale with latitude and longitude and plot the actual cores on top that you saw. 3JS is a 3D renderer in the browser that takes that XYZ data, plots it in 3 dimensions, and then gives it a color. So we use that to create our 3D render scene with lighting effects and controls and all that.
And in terms of the directions for future work with this tool, I think the first big piece is integrating with the existing ecosystem of tools, which the core view that Adam was showing off starts to do, so that the users can actually analyze the cores that they've already gotten, in addition to using this awesome 3D interpolation view. The second piece would be just providing more robust comparisons and annotations. So allowing users to not just save cores, but actually save out those maps with annotations, the full interpolations and the entire file, so that they can easily share and kind of compose almost like a mood board around sites and collect all the information in one place. And then thirdly, the interpolation methods that we're using right now are natural neighbors and linear. And I think that that's sort of a great start for this, but it would be good as a next step to incorporate more domain-informed approaches like nutrient flux modeling, which we know that the team is already working on. So we've kind of built this with the vision that they can incorporate that in later and actually load in their own interpolation methods. And finally, a really awesome future direction that we'd be excited about is informing autonomous space sampling missions. And this is like basically understanding how DeepSee gives humans the information they need to select sample sites could really help us inform how we train autonomous sampling systems on other planets. So kind of taking that human decision-making and transitioning it to be more autonomous. And another next step we're really excited about is to actually see DeepSee tested out on an upcoming cruise. And I believe the team is planning a cruise soon to Pescadero. So we're excited to see how that shapes up with DeepSee. And again, just to summarize the contributions that we were able to make this summer, before the team was literally just scanning an Excel sheet of values and kind of just looking for places where the numbers started to drop off to see those gradient drop-offs that Adam was showing. And you saw in the demonstration how DeepSee, with visually seeing those gradients in 3D and being able to fill in the gaps between these sparse cores, you can actually really get a sense of the spatial depth and the location that's pretty much impossible to see in a spreadsheet without familiarity of the area and actually being on the cruise. So yeah, I think we're really happy with the contribution we were able to make. And we just wanted to thank the team. So Haley, John, Victoria, and the entire Orphan Lab. They put in tons of time with us. And yeah, really helped us through all these iterations, make the tool much better. And thank you also to Haley for the inspiration for the name DeepSee. And finally, thank you to our mentors, Hillary, Santiago, Maggie, and Scott for their support through the 10 weeks that we worked on this. Yeah, and we open it up to questions again.
So I'll start off by saying I'm so blown away by what you all were able to put together in 10 weeks. And it really, every time we have this opportunity to spend an intense amount of time with you all, we really grow in our ability to think about our science. So it's not only, you know, explaining to you all what we do, but it also helps us think about our data in new ways. And as you mentioned, we have these opportunities to go to sea and really test this out in a pretty short time window. And so I'm very excited to be able to take this tool to explore these deep sea vents off the Gulf of California. And I think it's going to be not only valuable for our work, but I think as the oceanographic community starts to integrate these kinds of tools together, the geochemistry, the microbiology, the mapping data, this is really going to be, I think, transformative for the field overall. And so I'm hoping we can make this tool sort of widely accessible, and we're sort of working with all of you beyond this project, hopefully to pull that off. So thank you guys very much.
That's incredible to hear that, Victoria. Obviously, we think our interns are extraordinary designers and computing scientists. But when you talk about like transformative for the field, I think that's something that we can only really gauge when we're getting to those final iterations. And we recognize that these patterns and models are extensible. So for example, the interpolation methods, bring your own interpolation method and still be able to run it. And I really commend your team for helping our students understand the science, but also the techniques and methods about what matters and why. So thank you.
Yeah, just to add to that, I think Noah and I were reflecting on how much better just how much we've understood about your work and how far we've come in the last 10 weeks. Like it's incredible to start from knowing nothing about deep sea sampling and now understanding like, oh, you're looking for sulfide because it correlates with this type of bacteria. Yeah, and I think we'd like to open up to questions, but we can kind of speak to some of the exciting moments in our process if there are none.
We do have a question here about some of the decisions behind tool selection and how do we create, I'm guessing by sustainability, that we might be thinking about its actual implementation in a kind of hardened software environment. I wondered if we could talk a little bit about that.
Is that a question for the interns or for the mentors? There might be a different explanation depending on who you ask.
Yeah.
I think from the intern side, we're working on getting to the 10-week mark and having something to show. This sometimes requires us to really focus on that word prototype and create some value where there was none. Like there was blank space. And then what you saw on the screen from Jasmine, from myself, from the designers is from nothing. Like that's huge, but that also means that there's going to be those trade-offs of, hey, we had to hard code some things, we had to hide them away. So we might be thinking long-term, but I think the interns are really brought in to say, just get something on the screen so that we can show you guys something and start the conversation and keep it going.
This is Paul Rosen, so let me just, I asked the question, that's PA Rosen. So that's a good answer, but I'm wondering if in getting to that point of, oh gosh, we have to do something in 10 weeks, got to pick something. Did you even consider whether the tools that you used were sustainable or not long term?
If I could jump in, I view this in a couple of ways. From the perspective of the tool itself, the contribution is the design insight to the problem space, but at the same time, it's built on this technical background, back end, and there have been so many open source contributions that we're building on top of. So I would want to contribute back to the open source, but in the context of the prototype, this isn't necessarily code that is literally going to be reused. It's proof of concept.
Thank you. I understand. You can only do so much in 10 weeks.
Yeah, Paul, I think it's a really interesting question. And I think the way that we've generally tried to observe it, as I think we've gotten more mature in how we actually work in the program, has been that, you know, what we're really looking for is kind of figuring out, is there a space that we could really develop a really rich set of ideas, and effectively then we'll use the prototype as evidence to be able to find follow-on funding to then really work out the computing science of building a sustainable tool. And so effectively, it's kind of like an incubation period where we say, is there something that we could use that would justify the cost that we know building a tool in the way that you're describing would actually require?
Yeah, I fully understand that, and it's a great philosophy, and it's I think you've succeeded at least with these first two and probably the third as well. Very exciting. It's just always getting that next level of funding that's the hard part.
Yeah, exactly. And I think one of the things that we're learning as we have been able to spend more time doing this is where the potential leverage points can be. And I think we've actually, you know, certainly in the last 5 years or so, had at least 1 to 2 of the projects be able to continue on for, you know, between 1 and 5 years, and really be able to find that follow-on funding. And I think, you know, that you're right. Like, of course, finding money is the strangely time-consuming task for the sciences, without question. But I also feel like as we're able to show that the prototype can really be transformative, it's actually become a very strong argument towards getting that you know, follow-on funding. And so, I mean, the example I could share of some of the projects where we've been able to succeed towards that was to be able to get several AMOS proposals to work on software projects that were then folded into projects that serve JPL and open source communities such as Monty. And the work that I'm actually continuing now through a partnership with the Pixel instrument is now going on 5 years, and we'll have raised on the order of $1.5 to $2 million through Mars 2020 to actually make it a tool that's used in science operations on a day-to-day basis from the project. And that's one project within Mars 2020. We actually had a separate thread for rover drivers that I think had a similar long-term horizon. So of course, having a flagship mission can really give a lot more resources, but you know, in general, it's finding great science questions that's the most exciting thing for us, and then figuring out where those leverage points are. And I think we've been getting better at it.
Excellent. Thank you.
I think I can add a little more to that too. Is I think especially on the CALTECH side, we're also starting to build a methodology where we are very nimble with our students. We're interns saying, you know what, just come with the tools that you have and learn what you need as you go along, and we'll figure out how to do this. And through the iterative process, they come up with really refined solutions. But that also means adapting to new tools and new environments as they go along. And our students have, you know, from 5 years ago when we did the first Mars Relay, they brought React and they brought other JavaScript-based tools into the mix that themselves are learning in school. So the tools that we create, while they are just prototypes, they're so close to a working tool that with a small investment, we can usually tweak this prototype to be a slightly better working prototype. So we're starting to find this model where the students will work for the 10 weeks, then there can be a small follow-up to kind of tweak and enhance these tools just enough to make it a little more serviceable, a little more workable, and really start kind of opening up the venues for applying for grants and funding, saying, look, that's what this is capable of doing. So I think we're starting to figure out how to do that a little more regularly. So that's really nice.
I'd also want to add that in the 10 weeks, while we have this collaborative design and development process, we haven't done kind of beta testing out in the field on real projects that are, so for example, I'd look to Victoria's team, but the design of this tool set that you just saw, we worked on what would it mean to do it offline rather than the browser, on a client that could sit on an iPad or some kind of device and actually go out on one of the boats and actually test out some of the hypotheses, not about the data visualization per se, but about the use cases and the actual usage patterns and what we learned from that. So before we would refactor and harden something into a production ready tool, we'd also want to include that cycle of integration with real models from the lab going out into the field.
Yeah. Maybe just to add one other thing to what Maggie was saying, because, for example, we were able to actively evaluate and assess the efficacy of the tools that we're able to use, or when we can then actually make an empirical statement about a return on investment, which is, I think, an actual very important part of making that funding request. And so I was able to, for example, show with the tool for Pixel that, you know, with the automated anomaly detection feature that we were looking to build in, that actually after just a few anomalies, it pays for itself, because you're looking at, you know, just being able to just estimate the amount of time that it would have taken versus the time that the tool saves. So I think having data like that allow us with each of the different insights. Anyway, it's a very exciting thing to have asked. Maybe before jumping on, it looks like there was one other question. Maybe this is a good question for Adam about the modeling.
Can I just say one last thing, Scott?
Oh, sorry. Yeah, I didn't mean to run there again.
That's okay. I want to just say this is really brief, but just to say that this kind of question is actually really satisfying because, you know, as an artist, for me, this whole endeavor is a process of creative envisioning. And if you see potential and say like, can we actually do this? Then that's actually a success, right? Because it shows something that we get excited about that is possible and that we want it to actually have happen. That's like, you know, we show the picture of what could be, and then people say, let's make it work. So that to me is like, that's what we try to do. And then how do you make it work? That's where the next part of the hard work is, but our skills are in creating that moment of seeing the potential. Anyway, that's all I wanted to say. And Santiago, I wonder if I know you're sort of watching the clock, so do you want to tell us whether we have time for more?
Let's go ahead and answer the question that's on the chat. I don't know if Adam or Haley can answer the question. Is how do you handle interpolation when you have missing data? Like some of the cores that you showed were missing some horizons.
Mm-hmm. Yeah, that does bleed a little bit into that open source question too, which is that we use that what Malika described as natural neighbors and linear. We're very naive. Like whatever data is there, it like draws lines between them and then fills in the spaces. And with the natural neighbors, actually, we'll take the value and then propagate it out and then blend. It's super simple, naive, and that's actually one of the discussion points for the open source, because we realized how naive that was. And yes, it does not care about depth. It just says whatever's there, fill it in. When you notice that, and you notice an opportunity to have something more robust, what I would do in the code, and I'm sure Jasmine did and the designers did as well, was kind of just put a insert here, like put your model here. So I introduced as many of those as I could, where their team, specifically for Oceans for this one, can say, all right, we want to update how the interpolation runs. That is a clearly marked file right here that you just change and then just hit run and the tool pops back up again. And I've tested that part many, many times. So it was like trying to point out as many of those, if this does take off, what can we, what would have to do, what would we have to change next? What would have to be updated? So yeah, we don't include that now, but imagine that we could, it'd be very easy and extensible from the way I developed it to make that happen. So.
Thank you, Adam. So we'll have a larger period for general questions and answers also at the end of the third presentation. So let's go ahead and move to